Let's consider a few number system definitions. These are just some common definitions that you'll hear talked about in a math course. We define the natural numbers, denoted by this script n, as the set 1, 2, 3, 4, all the way out to infinity. We also define the whole numbers, denoted with this script w, as the set of all natural numbers, and you just throw 0 in with it. So 0, 1, 2, 3, 4, all the way out to infinity. We define the integers, z, to be the set of all positive and negative natural numbers, along with 0 thrown in. Then we define the set of all rational numbers, denoted by q. Now that's the set of all fractions or quotients involving integers. So for example, numbers like 2/3, -5/4, 1,235 divided by 207, these are all rational numbers because they're the quotient of two integers. Now you might have heard of an alternate definition for rational numbers. You can also define them to be the set of all numbers with a decimal expansion that either repeats or terminates. Now any number with a decimal expansion that either repeats or terminates can be written as the quotient of two integers. We're not going to prove that here, but it is a fact. For example, 0.5, that terminates, just 0.5 and then nothing. That's, of course, 1/2, 1 over 2. So that's the quotient of two integers. 0.333 repeating like that, that repeats, and we can write that as 1/3, quotient of two integers. Even a number like 23.4545 repeating like that can be written as the quotient of two integers. You can check it out. It's actually equal to 2,322 divided by 99. Just evaluate that on a calculator and you'll see that you get the 23.45 repeating. Now just some more notation here. Sometimes you'll see 23.4545 repeating like that written as 23.45 with a little bar over top of the 45. That just means that the 45 just repeats. We also define the irrational numbers. Now the irrational numbers are sometimes denoted with this script I, and they're the set of all numbers with a decimal expansion that does not stop and does not repeat. In other words, they're the set of all numbers that cannot be written as a quotient of integers. The most famous irrational number is probably pi, 3.1415926, and it just keeps going. The decimal expansion never repeats and it never stops. Another one would be the square root of 2. Square root of 2 is 1.4142135562, and it just keeps going. Never stops, never repeats. Then we then define the real numbers, denoted by r, to be the set of all rational and irrational numbers lumped together. Now normally when we draw a number line, like when you see somebody draw a number line like this, this normally represents the set of real numbers. So we've got rational and irrational numbers lumped together in here. So that's how we define the real numbers. Now let's take a look at one of these numbers like pi, one of these irrational numbers, pi. That's such a famous number and it's so useful, and you'll see it come up in a statistics course. Let's recall how that is defined, what it exactly is. Now here we have a circle and we have a diameter cutting across the center. Say that is just of length d. That's the diameter of the circle there. Pi is simply the number of times you can take the diameter and lay it around the outer edge of a circle. So in other words, you can take this diameter and put it around the outer edge 3.14159 times. So if we took this and just laid it around the outer edge, it would go around once, twice, 3 times, and then what you'd have remaining here would just be the 0.1415926 ... times d. So you'd have 1d, another one, and then 0.1415926 of the diameter would be left over right here. So that's all pi is, and it can be shown that it is actually an irrational number. Let's take a look at some common math symbols now. So these are just some symbols that we'll be using. We have the equal symbol, you should be familiar with. So that just means two expressions on either side are the same. For example, 4 equals 4. The not equal to symbol is just the equal with a slash through it, and that means that two expressions are not equal or not the same. For example, 4 does not equal 5. We then have addition, which you should be familiar with, and subtraction. So 3 plus 5 is 8. 5 minus 3 is 2. Now multiplication, we have some different symbols we can use. We'll sometimes use a dot or an asterisk. Now the asterisk you will normally see when you're typing something into a calculator or computer. Oftentimes you'll see the asterisk displayed for multiplication on a computer or calculator screen. You also have the standard cross symbol like that. Now that we don't use very often in math courses because it looks too much like the letter X, and we want to reserve the letter X for a variable, so we don't use this very often. We usually just use the dot symbol. Or sometimes if you have something like, say we have a variable X and we want to multiply it by 2, sometimes we'll just write 2x like that without the dot there. And that just means 2 times x, or 2 x's. So we sometimes leave the dot out. Now there is a dot there that's implied, but sometimes you won't see that written if you see a variable, or you might see 2 times a, 2a, or 2 whatever the variable name might be. So for example over here, 3.5, that means 3 times 5, or 15. 3 with an asterisk or star like this, 3 asterisk 5 is 15 as well. And then of course 3 times 5 here is 15. Division, you'll see that we use the slash symbol usually, the forward slash like this right here. We don't really use this one very often, the old sort of minus with the 2 dots above it to denote division. We don't use that, but of course it does mean division. So for example, 12 forward slash 4, that means 12 divided by 4, or 3. Now of course we'll sometimes write it like this with a horizontal bar. Right, so we will sometimes use that as well to denote division with the 2 numbers above and below. So 12 over 4 means 12 divided by 4, or 3. And then of course you have the other division symbol like this, 12 divided by 4 equals 3. But we don't use this one very often. Usually it's just the forward slash or the horizontal bar. Now this one, the hat symbol, is used to denote exponents. For example, when we write 3 hat 2, that means 3 squared, or 3, you see 2 is in what we call the exponent. It's in a superscript right here. We call that the exponent position. That means you multiply 3 by itself 2 times. So this means 3 times 3, which is 9. Now that hat symbol, usually we write 3 squared like this. We don't usually write this. Usually this is reserved for computer and calculators. If you look on a calculator, you'll see a hat button on it. That means exponent. And when you type it in, you'll see it written like this on the computer screen. The same with Excel. If you evaluate 3 hat 2, you'll see the hat symbol appear, and that means 3 squared like this. We also have the less than and greater than symbols. So, for example, 3 is less than 5, 7 is greater than 2, and then we have the less than or equal to down here. You just take the less than and put a little bar underneath it, and greater than or equal to symbols. So, for example, 3 is less than or equal to 5, 7 is greater than or equal to 7. We also have our approximation symbol. So that means two expressions are numerically close to each other. For example, 5.1 is approximately 5. Pi is approximately 3.14. So that's how we use our approximation symbols. So those are a few common math symbols there. Now let's recall how we round numbers. A decimal number may be rounded to the nth place by considering the value of the n plus first position after the nth decimal place and applying the following rules. If the n plus first value in the decimal expansion is bigger than or equal to 5, we will add 1 to the nth value and then chop the decimal off after the nth position. On the other hand, if the n plus first value is less than or equal to 4, like 0, 1, 2, 3, or 4, then we leave the nth value as is, and then we just chop the decimal off after the nth position. So that's how we round numbers. Let's take a look at 2 examples here. So for the first one here, we want to round this to the second decimal place. So we look at the third decimal place, that's the 6 right here. That's our third decimal place, and well, that is bigger than or equal to 5. So we add 1 to the second decimal place, make the 4 a 5, and then we make that a 5 right there, that 4, and then we just chop everything off and we throw away the 6, 3, 2, 8, 9. So then this would be rounded to 2 decimals. It would be approximately 23.35. And there it is rounded to 2 decimal places. Let's take a look at this one. So we have 4.563219990. So we want to round it to the second decimal place. So we look at the third decimal place, which in this case is a 3. Well, that is less than or equal to 4. And so we go to the second decimal place, which is a 6 in this case, and we just leave it as a 6. We don't change it. And so then we just throw away 321990, and we would say this is approximately 4.56. And there it is rounded to 2 decimal places. So that's how you round numbers. It's fairly easy.